Yeah, so now let's move to the part where we'll be trying to solve the pressure drop for or pressure drop due to friction, right? Where we have a straight pipeline or where we can have some miscellaneous equipment, meaning we have fittings, we have valves and all those things, right? So from here, for you to evaluate the pressure drop, right, in a pipeline or in a piping system, that means that you have two methods that we can use. You have first what we call the equivalent pipe diameters method, right? And we have the second one, which is called the velocity hertz method. So for the equivalent pipe diameters method, that one we try to make sure that the fittings and the valves, I mean the miscellaneous equipment in the piping system, right? You try to find an equivalent length for them. You get it? So from a table, right, we can read the the equivalent pipe diameters from there, from that table. So each of them, so if you take a plug valve, right, which is fully opened, we can have its value. Then if you take let's say an elbow, right, or a standard elbow, right, you can also have its value that we can use to evaluate the equivalent pipe diameters method, right, making our thing very easy to work with, right? Do you get it? So right now, let's start with the equivalent, and then for the velocity yes method, that one we try to evaluate the pressure drop due to just the straight pipeline. Then we try to evaluate the one due to the miscellaneous equipment. Then we add them, right, to get the total pressure drop. That's for the equivalent. That's for the velocity hertz method. So right now we start with um the equivalent pipe diameters method. But for you to even calculate for the pressure drop, right, we have the formula HF L on D times the density multiplied by V squared divided by 2. So this formula is for so this formula over here, right, is due to the Moody chart we are using. So when we are reading the Moody chart from any reference material, you make sure that you use the equation that has been assigned to that Moody chart, right? Because the friction factor there can either be a Darcy friction factor or the Fandom friction factor, right? Yeah, so that's the relation you're going to use to solve for the pressure drop, right, in the piping system. Yeah, so that's the equation you're coming to use, right? So we have, and depending on the type of material that's being stated in the question, we can actually get the absolute roughness, right? So we know that the relative roughness is what we need for us to read the Moody chart. So it's equal to the absolute roughness divided by what? The diameter. And we read the internal diameter. The internal diameter that you always have to use to solve what your question. You get it? Because the internals where the friction what occurs. Right. So it's always the internal diameter that we use over here. So for the but when we give you an outside diameter, if you want to get the internal diameter, we have to subtract two times the thickness of that pipe. So if you subtract two times the thickness of the pipe from the outside diameter, we get the internal diameter of what of the pipe. That's what we use to solve our questions, right? So and over here too, since we are evaluating the power, we are evaluating the pressure drop. We also be evaluating power to due to the pump or whether we are using a turbine, and we also be evaluating MPSH, right, for all these questions, right? So right now let's start with the question number three. Right, so let's start with question number three over here. So question number three, we have water. Right, so they give us the volumetric flow rates, right? So to be 1,250 centimeter cube per second, right? So water is pumped, right, through a steel pipe, and the steel pipe is they has a diameter of 25 millimeters and a length of 30 meters, right? So as you can see from the question over here, the internal diameter is 25 times 10 to the power minus 3 meters. Then I have the length to be 30 meters, right? Then I have the change in Z over here to be what? My 12 meters. but it's negative 12 meters. Why is it negative 12 meters? Because the change in Z over here is Z1 minus what? Z2, right? And if you are looking at how we are pumping the thing, we have the reservoir over here. So we have the water level, then we have the pump right over here. So this is the discharge side, then to the where we are delivering the thing to. So they said that there from there to you have a tank height of 12 meters, which is higher than its reservoir. So this is the reservoir. So from here to here, and the distance there it comes at 12 meters. Right. So if you have 12 meters and I have Z1, which is the reservoir over here. So that's my reference point. So you come 0. Right. So it's 0 minus Z2, which is 0 minus 12, which is negative 12 over here. Yeah. So that gives me that one. And viscosity, right? We have the viscosity to be 1.30 times 10 to the power minus 3 because of the milli there. Then the unit Newton second per meter square. Right? So that's the viscosity. Then we have density of the water to be 1000 kilogram per meter cube. Right? So we have all these parameters. So the question 2 is telling us to calculate for approximate power watt, which is required, right? So first of all, if you want to find the power over here, there is this relation we have to use. So we use the relation G, change in Z, right, plus the change in P over rho minus change in PF divided by rho minus W equals 0. So using this relation, you can actually calculate for the W, which in turn will help us to calculate for the power of the pump, right? So over here, first of all, we need, and this P, change in P over here is P1 minus P2. And since we are considering this system, right, we assume that where the reservoir is and where we have the delivery side, they are all experiencing atmospheric pressure, which is 1 atm, right? So that means that P1 will cancel P2 because they are the same thing, which is 1 atmosphere, right? So this is the relation you have to use, and from this relation, that means that we need change in PF, right? That's the pressure drop due to earth friction. So we need to go back to our methods, whether we are using the equivalent pipe diameter or the velocity hairs. But this question is very straightforward since we don't have any fittings or we don't have any miscellaneous equipment. So we are just evaluating for the pipeline. You get it? So the so just evaluating for the pipeline. So over here, since we have all these things over there, that means that we need to find our change in F, and from the formula that was given, we need to find the friction factor first. Right, so help us to find the change in P. Then we can actually continue. But before we can find the friction factor, we all know that the friction factor depends on the Reynolds number and the relative watt roughness. So you need to find Reynolds number, then find relative roughness. Then you can read from the Moody chart to actually get the friction factor and calculate the pressure drop. So over here, we know that they give us the volumetric flow rate, right? So the volumetric flow rate is 1250 centimeter cube per second. That's converting it to meter cube per second. We get 1.25 times 10 to the power minus 3 meter cube per second, right? So that's the volumetric flow rate. And from the volumetric flow rate, you can actually find the velocity since we need velocity to calculate for the Reynolds number. So we have to find the area first. So the area becomes pi d squared on 4, and the diameter was 25 millimeters. The diameter was 25 millimeters, which is this that value over there. So this one squared divided by 4. Right, so the area becomes 4.9087 times 10 to the power minus 4 meter squared. Right, so having this as the area, I can calculate my velocity as the volumetric flow rate divided by area. So having a value 1.25 times 10 to the power minus 3 divided by 4.9087 times 10 to the power minus 4, which gives me a velocity of 2.55 meter per second. Right, so if I have the velocity over here, meaning that the Reynolds number will be easy to calculate for. So Density was 1000, velocity is now 2.55, diameter is 25 by 10 to the power minus what? 3. Then the viscosity given in the question is 1.30 times 10 to the power minus 3. So this gives me a Reynolds number of 49038.46, which is approximately 4.9 times 10 to the power 4. Right, so I have the Reynolds number. Then for me to calculate for the relative viscosity, relative roughness is the absolute roughness divided by diameter, right? And we can get the absolute. And over here they said we are using a steel pipe, right? So if you're using a steel pipe, there's a way to get. So there's a table where we have to get the where you can read the roughness from Y. So if I check this table that I have over here, right, I can see that a steel pipe has an absolute roughness of 0.046, right? 0.046. So if I have the 0.046, meaning that I can actually calculate for my relative roughness. So you can 0.046 divided by 25, and absolute roughness is in millimeters. So you can just leave your inside diameter in millimeters too. So having roughness of 0.00184, which is approximately 0.002, right? So using this relative roughness and the Reynolds number over here, you can actually read the Moody chart to get our friction factor. So from the Moody chart, using those two, the friction factor becomes 0.026, right? So since we have our friction factor now, you can actually go on to calculate for our pressure drop, right? I find our pressure drop. So over here, the pressure drop becomes 8F, right? So the F is 0.026 times the length was given as what? The length from the question was given as 30, then divided by diameter 25 times 10 to the power minus 3. Then we multiply this one by the density times the V squared, which is 2.55 divided by 2. So this gives me a pressure drop of 811,512 Pascal. Right, so this is the pressure drop due to what? Friction. Right, so I have the pressure drop due to friction now. So since I have this one, I can actually go on to calculate the power in the pump, right? So as I said, G change in X, right? Then we have plus the change in P divided by rho, right? Minus change in PF divided by rho minus what's W equals 0. So over here, I said this part becomes what? 0, right? Because the P1 minus P2 is 0. P1 and P2 is the same thing, so 1 atmosphere. So that place with 0. And over here, I have 9.81 multiplied by minus 12, right? Then the PF is 811,512 divided by 1000 minus what? W equals 0. So over here, W will be equal to negative 929.232 joule per kilogram. Right, so since we are getting negative, that tells us that it's actually a pump that you are using. If you get W to be positive, that means that you are using a turbine. So the formula becomes the mass flow rate, the power over um, the efficiency. But if you get positive W, meaning you're talking about a turbine, then the power becomes the mass flow rate times the work times what? The efficiency. So you have to know the difference between them, right? So that you won't make a mistake, right? So for a pump, it's divided by the efficiency, but for a turbine, it's multiplied by the what? Efficiency, right? So based on that one, since you are using this one, since this one, it says if you find the approximate what power, since the efficiency wasn't given, so assuming 100% what efficiency, right? So we assume 100% efficiency to solve for the power, right? So the power becomes, so you need to find the mass flow rate, right? So you know the mass flow rate is equal to rho VA, where the VA gives us the volumetric flow rate, right? So much easier. So 1000 multiplied by 1.25 times 10 to the power minus 4, and that gives me the sorry minus this minus 3. So the mass flow rate becomes 1.25 kilogram per second. Right, so that means that the power now becomes 1.25 times 929.232. And the reason you are putting the work inside the formula, you can ignore the negative. Divide by 1. The efficiency is supposed to be in fraction, right? So it's divided by 1. So this gives me a power of 1161 point um, point 0.5 watts. Right, so I have 1.2 watts kilowatts. Right, so this is actually how to solve for at the power, right, for this question. So it's very easy, and please make sure you don't make any mistake with your change in z, because that's where everything can go wrong. If the change in z is supposed to be negative and you make it positive, you actually get a negative answer for the w, negative like 600 and something, but it's wrong because the change in z is z1 minus z2, right? So it's actually supposed to be what's negative, right? So you get it that way, right? Do you get it? Okay, sure. So right now let's move to a question that where we'll be applying the equivalence pipe diameters method, then the velocity hertz methods too, right? So over here, let's see question number 1 from the past question over here. Over here, the question number 1 over here is telling us that a pipeline connecting two tanks contain 4 standard elbows, a plug valve that is fully opened, and a gate valve that is half what opened. So first of all, we'll be using um the equivalent what pipe diameter methods first. So over here, what you do is that you draw your table. So in the table, we will have the fittings, right, or the valves. Then we will have the equivalent what pipe what diameters over here. You get it? So the fittings that we have over here, we have standard elbows. We have 4. So you have the standard um elbows. You have 4 of them. So 4 times a certain number. Then we have a plug valve, right? So they said that the plug valve is what fully opened. Now you have a value for it. Then we have a gate valve, right? Then we have a gate valve which is also half opened. And please, when you are solving all these questions, make sure that you have to always add your tank inlet and tank outlet. You have 2 tanks, they'll have an inlet and outlet. So please always remember to add them. Alright, so we have the tank inlet, then we have the tank outlet, right? So we'll be getting some values for them too, right? So that one too, we have a table that we also read that from. So let's see. So that one, we have a table that we also read all those values from. So based on that table, we can actually get them. So based on this table, we can see that the standard elbow, right, has a number of equivalent pipe diameters of 15. Then we can see the plug valve, which is fully open, also has a value of 18. Then a gate valve, which is half open, has a value of what, 200. Alright, so based on this table, you can actually get all those values, right? So based on that, we see that the standard elbow was 15, the plug valve 18, a gate valve which is half opened is 200. Then I said the tank inlet is 50, then outlet is what, 25. So the total over here gives us 353. Right. And when we see this one, we need to calculate what the extra length, right? The extra length given by the miscellaneous equipment, right? So the extra length becomes the number of equivalent pipe diameters multiplied by the pipe internal diameter, right? So from this question, they told us the diameter is 25, right, millimeters. So this gives us an extra length of 8.0 825 meters. Right, so that means that the equivalent length for the piping system becomes the total length of the straight pipeline, which is 120, plus the extra length, that's the length given by what the miscellaneous what equipment, that's the valves and what the elbows. So this gives us 128.825 watt meters, right? So we need to get all these values. Then we just add them, right? And they give us a certain mass flow rate, right? 3,500 kilogram per watt. Right, so 3,000, this one per hour, right? Then we get we divide by 3,600, right? That gives us the mass flow rate of so we need to get the mass flow rate, right? Sorry, they give us the mass flow rate over here, so we need to get the mass flow rate from that question. So when we divide, we get 0.972 kilogram per second, right? So you have the mass flow rate now. So that means that we can actually go on to calculate for the change in P, right? The power, sorry, the pressure drop. Where we still need to go back to our Moody chart. So we need the area, we need velocity to get the Reynolds number exactly, right? So the Reynolds number is rho V d over mu, where we need the, so we know that the mass flow rate equal rho VA. Right, so velocity gives us the mass flow rate divided by the density times what the area. So this is where I need the area, which is pi d squared divided by 4. So the d over here is 25, right? So minus 3 squared divided by 4. That gives me, and please make sure your area is always in 4 decimal places. So 9087 times 10 to the power minus 4 meter squared, right? So this is the area. So upon getting area, the area, we can actually calculate for the velocity, which is the mass flow is 0.972 divided by the density was given as 998. Then the area is 4.9087 times 10 to the power minus 4. Then our velocity becomes 1.98 meter per second. That's very easy, right? So right now the Reynolds number becomes the rho Vd divided by mu. So the rho is 998 times velocity, which is 1.98, times diameter, which is 25, times 10 to the power minus 3, divided by, this one was given as 0.99 minus 3 because of the milli. So the Reynolds number now over here for this question becomes 49900, which is approximately 5.0 times 10 to the power 4. Right. And over here, since they said we are using a commercial steel pipe, so it's also the steel pipe, so it has an absolute roughness of 0.046. You get it? 0.046. Right. So still using, so that means that the relative roughness becomes 0.046 divided by 25. Right. That gives us 0.00184, which is approximately 0.002. So based on this one from the Moody chart, the Reynolds number becomes from the friction factor becomes 0.0258, right? So then the pressure drop, right, due to friction now becomes 8 times 0.0258 multiplied by the length. But the length here now becomes what? Equivalent length, which is the this one. The equivalent length is the length of the pipe plus that of the miscellaneous equipment, the fittings and the valves, right? So we have 128.825 divided by the diameter, which is 25, times 10 to the power minus 3, by density, which is 998, times 1.98 squared divided by 2. So this gives us a pressure drop of 2080658.29 Pascal, right, which is 2.1 watts megapascals, right? Yeah, so this approach over here, right, is what you call the equivalent what length what pipe diameters what method. This approach is what you call it like that, right? So now let's see how to use the velocity hairs method to also calculate for that same what pressure drop. You get it? The velocity hairs method. So um now one to so we have the velocity hairs right method. That one too, you see the table that we had. So we have the fittings, right? Then we have the key values, right? That's the values that you're reading, right? So over here, when you check that table that we used, you can see that the standard elbow we had four had a value of 0.35 from that table. That's using a velocity here, 0.35. Then the plug valve, which is fully opened, right, had a value of 0.4. Then the gauge valve, right, which is half open, had a value of 4, right. Then I always tell you your tank inlet and tank outlet is very important. Tank inlet, then we have the outlet, right. So the inlet is 1.0, outlet is 0.5. So adding everything over here, we have what 7.3. Right. So based on this method, when you actually calculate for your velocity head, right, which is 7.3, we need to calculate for what we call the velocity head. Right. So we know that the um we need to calculate for the velocity head. Right. This is the number of velocity heads, which is the key. So now the velocity head is v squared over 2g. So that's the formula. And we know that we got a velocity of 1.98 from the first one. So that's the same velocity. Yeah, by 2 times 9.81, right? So this gives me a velocity head of 0.200 meters, right? But we need to actually calculate for what the total head, which is each. So the total head actually over here is the velocity head multiplied by the number of velocity heads, which is so the number of velocity heads, the total is 7.3 multiplied by the velocity head, which is 0.2. So this gives me a total head of 1.46 meters, right? So if you have this one, we can you see this one, the number of velocity heads are using over. We use now to evaluate just for the fittings, right? So the pressure drop due to the miscellaneous equipment becomes rho GH, right? So the rho over here was given as 998 times gravity 9.81 times the total head, which is 1.46. We are converting the head to what pressure in Pascal. So we get 14293.95 Pascal, right? So this gives me the pressure drop for just the miscellaneous equipment. So that's the difference between equivalent pipe diameters and velocity heads. Velocity heads will just calculate for the fittings, they calculate for the pipeline, then add. But equivalence pipe diameters add the two, right? You may add the two to calculate for it. So over here, we actually have to also calculate for the change in P for the pipe, right? For the pipeline, which is 8F L on D. So this L won't become L equivalent because you're using velocity here is rho V squared divided by 2. Right? And here we know that 8 times the same friction factor 0.0258. Then the length was given as 120. That's the length of the pipe itself. Then the diameter, then the density, then the velocity. Right. So this one over here gives me a pressure drop of 1938125.325 Pascal. Right, so if I get this one, I'll know that now the pressure drop due to friction becomes the pressure drop for the miscellaneous equipment plus the pressure drop for the pipeline itself, right? So for the miscellaneous was 14293.95, and this one is 1938125.325. So this gives me 19381 0.8125. So this gives me a certain value, right? This gives me a certain value. This gives me a value of so I have 8, right, multiplied by 0.02258 multiplied by 120 divided by 25 times 10 to the power minus 3 times 998 times 1.98 um times 1.98 1.98 squared, right? So this gave us all right, this gave us a value of 1932299, right? 0.297 Pascal, right? So adding that value, right? So adding this value and this value, right? We get 1938125.325 watt Pascal, right? So it gives us so over here which gives us 1.9 megapascal. Yeah, 1.9 megapascal, right? Or 1.94 megapascal anyway. So which is closer to the 2.1 watt megapascal from the equivalent pipe diameter. So these are the two methods that we use, right, to actually solve for the question. So right now we move to a question where we have to calculate for the MPSC. So now we've looked at the power. So I told you the power. If you get negative work, that means it's a pump. If you get positive work, that means you're using a turbine. So the formula for the power would differ, right, based on the one that you are getting. So right now, let's move to a question where we'll be solving for MPSH.